Okay, well, thank you. I'm very grateful to the organizers for the opportunity to speak and to try to learn something about complex and algebraic geometry, which I know very little about. But so last night at dinner, I mentioned to my kids that I was coming to lecture at Harvard this week, and I don't think I could say Harvard, but and my 12-year-old, his eyes opened up like this, and he said, "The Harvard?" And I said, "Yes, the Harvard." Anyhow, so I'm going to talk about joint work with Simone Brendle and Flavien Leger and Cale Rankin, which appeared a couple of years ago. And it's also based on earlier work by Young-Hyun Kim, and who's in the audience today, and Micah Warren on this geometrical approach to optimal mappings. And there is a version of these slides, and also the slides for the talks to my subsequent lectures will be posted on my webpage. So I think this one is just called Talk. Then there's like talk 1, talk 2, and talk 3. So I think tomorrow's lecture will be talk 3, and Wednesday's lecture will be talk 1. Okay, so here's the agenda for today. Is I'm gonna give this sort of brief overview of highlights of extremal surface theory. And then I'm going to talk about optimal transportation. I'm going to give a kind of introduction. Maybe there are some algebraic geometers in the audience who know as little about optimal transportation as I know about complex algebraic geometry. And so then I'll give an introduction to optimal transport. And I'm going to emphasize its links to differential geometry and topology and notions of curvature. Okay, so this is basically the plateau problem. And so if you think of the graphical version, you can fix a domain, omega, and you can imagine trying to find a graph with given boundary values that has minimal surface area. And so if you write this parametrically, here's an integral. I'm looking for a function u on the domain omega with given boundary data. And this is the expression I'm trying to minimize. And so the Euler-Lagrange equation for this variational problem is that the divergence of the derivative of the integrand should vanish. And things that satisfy this are called minimal. And if you imagine sort of taking blowing up around a point of a solution that satisfies this using the correct scaling, then you would get, after blowing up, you'd get a global solution on all of Rn, which satisfies this. And in less than 7 dimensions, global solutions to this equation on all of Rn were classified first in 2 dimensions by Bernstein more than 100 years ago, and then by DeGiorgi around a little bit before the time I was born, and then by Almgren. This was in maybe 3 dimensions, and then in higher dimensions by Almgren and Simons. But remarkably, also in 1968, which was a very good year, Bombieri, DeGiorgi, and Giusti showed that in higher dimensions, there are counterexamples to this, which are basically based on the Simons tone. So if you have R4 across R4, well, let me tell the story in 2 dimensions first. So if you have R across R, and you look at the circle, and you divide it into 4 quadrants, well, maybe, yeah, let me do it like this. And you ask for a function that's like 1 here and 0 there. There are a couple of different competitors. There's the one that's maybe 1 in this region and 0 here. And then there's also the guy that's 1 in this region and 0 out there. And there's the fellow that's 0 here and 1 over here. And in 2 dimensions, these guys have lower area than the original fellow that I drew. The fellow that was 1 here and 0 there. But by the time you get to R4 across R4, it turns out that this surface here with the singularity at the origin has lower surface area. And so things like this lead to counterexamples to regularity, to solutions to this equation, high dimensions. And then, so this is going to also, there's going to be a lot of echoes of the first unexpected echoes between Yang Li's talk this morning and mine. So if you look at higher codimension structures, so Federer also around the same time observed that whenever you have an analytic variety, an analytic or algebraic variety, algebraic curves even can have singularities in C2, let's say. But they're actually, the graphs of these analytic varieties are minimal surfaces in the sense they satisfy an equation like this. And so whereas in codimension 1, the singularities always have codimension 7. In a higher codimension, the singularities just have codimension 2. And this was eventually established in the famous Pothamus big paper of Almgren, which showed that right, when you look at the analogous minimization, higher codimension, you encounter singularities much sooner. Okay.
So Ron, before you change slides,
yes.
Should that power be -1 on RK?
I actually don't believe this is kind of,
Your slides.
I've written the blow up wrong. So really what I want to do is geometric blow up. I want to zoom in on the picture. So I need to take into account the graphs. I'm afraid I was thinking about obstacle problems when I wrote this. Yes, so what I did want to do though is I had this integrand on the previous slide, square root of 1 plus gradient u squared. And so if you think about the integrand, it's like the graph of a hyperbola. And if you Legendre transform this integrand, you get the convex conjugate would be something like this. And with the minus sign in front, its graph is a semicircle, and it jumps to plus infinity when gradient u crosses 1 in absolute value. So you could also try to imagine minimizing something like this, or if you drop the minus sign, that's equivalent to maximizing something like this. And that's a nice convex variation or concave maximization problem as well. And the Euler-Lagrange equation for this integrand is what I call the maximal surface equation. And I think of it as being a maximal surface equation because when you pass from this plus to this minus sign, it's like switching signatures from Euclidean signature to Lorentzian signature. And so this is really the area of the graph of U in Minkowski space. And so when you try to do this maximization problem with, say, boundary conditions, you're looking for a maximal area hypersurface in Minkowski space. But of course, gradient U has to have magnitude less than 1, which means that in the standard coordinates on Minkowski space, that's telling you that the U has a space-like graph. And so this is like maximizing the area of space-like hypersurface in Minkowski space. And you can do the analogous blow-up, hopefully written with the correct scaling, on this. And you would expect, as long as you start out with a point where the gradient is strictly less than 1, when you do the blow-up, you'll get a solution which is maximal throughout all of Rn. And you can wonder if there's a Bernstein theorem for this equation. And that thing was it was noticed by Calabi already in the year that I was born, that in 2, 3, and 4 dimensions, any entire solution that has gradient less than 1 to this equation is linear. And then Cheng and Yau observed that this goes through in all dimensions, actually. So it's somehow better. Now you're working with this Lorentzian background metric, and the regularity theory is in some ways better than it was for the Riemannian case because you don't have Simon's cones. And on the other hand, there are things that are more complicated about this setting. I mean, for example, the ellipticity degenerates when the magnitude of the gradient tends to 1. And another thing that is more complicated is that the symmetry group of Lorentz space is the Lorentz group, and it's a non-compact group. And so there's less compactness built into this problem than when you have a Riemannian background metric. And then there's also some orientation delicacies associated with the fact that you have future and past. And so you can also wonder, like Federer and Almgren's, about whether the analogs of Federer and Almgren's results in this sign background setting for higher codimension. And it turns out that a lot less is known. There was a PhD student of Reese Harvey in the early 90s who wrote a thesis about this problem. And then there's a survey by Harvey and Lawson a dozen years ago. But somehow this is an interesting problem for me because one of the things that I discovered with Jungton and Micah 15 years ago is that in the optimal transportation problem of Monge and Kantorovich, you can think of the graph of the optimal map as being a space-like area maximizing surface. But in the optimal transportation problem of Monge and Kantorovich, I'm going to imagine I have two domains, omega and omega bar, which are both in, let's say, Rn. And then I'm going to think of the product omega cross omega bar. So and I have a cost function or a benefit function, b of x bar on the product of the two domains. So often you try to minimize the cost. Sometimes I prefer to maximize a benefit. And so and I'm also going to be given densities, rho probability densities, let's say, and rho bar on these two domains, which integrate to one. And the Monge-Kantorovich problem of optimal transportation is, to find a diffeomorphism between the two domains, which push forward this density to that density. And among such things, I want to choose the diffeomorphism which maximizes the benefit function. So I have some something like this. And so the graph, if such a diffeomorphism exists, its graph is going to be some subset of, both of these are n-dimensional, so it's going to be some n-dimensional subset of a two n-dimensional product domain. And what we observed with Kim and Warren is that you can use the benefit you're trying to maximize to define a metric on the product domain such that this submanifold becomes zero mean curvature, maximal. And so there's somehow this unexpected connection between optimal transport on the one hand and extremal surface theory on the other hand. But the background metric that's going to come from our cost or benefit function is going to have signature NN. And okay, and so then the update, the new observation from a couple of years ago is that when you think about the regularity of this surface, there's a sign which is more favorable in this split signature than it was in the Riemannian case, and that it's basically, this is the key to deducing the kind of regularity results that Ma-Trudinger-Wang found for the optimal transport problem in 2005. Are there questions about the agenda? Yes.
I guess this is a stupid question, but would there be anything special if, from analysis point of view, if n and m are 3, 19?
If m and n are what?
3 and 19.
3 and 19.
Yes.
Okay, as soon as n is different from n,
Yeah.
then at least the kind of metrics that I'm going to define, I can do optimal transportation between different dimensional spaces. But the geometry that I'm going to define on those different dimensional spaces is going to, the signature is going to be degenerate in the sense that there'll be some time-like directions and some space-like directions and a bunch of zero directions. And the number of zero directions is at least the difference between n and m. And so, okay. Other questions? Okay, so now I'm gonna, okay, so this is good. So the next thing I'm gonna do is a little bit technical. It's probably perhaps the most technical thing that I will do today, which is I'm gonna have an excursion into the differential geometry of submanifold. And I need to fix a bunch of notation to do this. So I'm gonna have an ambient space with n plus m dimensions and a signature nm metric, which means there's n space-like directions and m time-like directions and no zero directions. And I'm going to be looking at an n-dimensional submanifold. And so I'm going to have this sign metric on the ambient space and its associated Riemann tensor. And the submanifolds of interest to me are going to be space-like in the sense that when I restrict the ambient manifold to the submanifold, it should be positive definite. And I'm going to use the hats for objects in the ambient space and without hats for the restrictions to the lower dimensional spaces, the submanifolds. And so maximal is going to mean that the zero mean curvature vector of sigma, which is the trace of its second fundamental form, vanishes, where the second fundamental form is this gadget that it takes two tangent vectors to sigma and it sends it to a normal vector to sigma. And basically it measures the difference between covariant differentiation in the submanifold and covariant differentiation in the ambient space. So the capital X and capital Y will be tangent vector fields on the submanifold. So this thing here is going to be my submanifold in the application. And so the lemma is the following. So I have this sign metric on the ambient space, but let me also have a positive definite metric, S hat, as well. and which I can diagonalize S hat using basis E1 to En, and I can diagonalize G hat on the ambient space. Sorry, I can diagonalize the restriction of S to the submanifold using these n basis vectors, and I can diagonalize G hat in the ambient space using the capital E's. And so the claim is the following, that if I look at the G Laplacian of S, and I evaluate it in one of these directions here, and I look at the ratio of that to S in the same direction, there's a lower bound for that, which involves a partial trace of the Riemann tensor where the trace is just over the submanifold directions, so the sigma n directions. And then there's some correction term with a constant in front of it, and that may be large, but the constant really, it only depends on these ambient objects, and it doesn't depend on which submanifold I've chosen. And okay, so the proof of this lemma is sort of a long computation. So you do this computation where you want to compute this Laplacian, and a bunch of terms vanish because my submanifold is assumed to be maximal, or vanishing mean curvature. And okay, so the first good news is that the mean curvature vector, which is always normal to the submanifold, the submanifold is spacelike, and there are only n spacelike directions in my ambient metric, so all the orthogonal directions have to be timelike. So this minus G hat in the normal direction is positive, so that's going to help my inequality. I can throw this red term away. And this is going to give me the partial trace of the Riemann tensor when I sum over the orthogonal directions EL to En on the submanifold. So this is a good term. And then the other terms, this thing, for example, has a good sign. It's positive. And this we don't know the sign of, but using Cauchy-Schwarz with epsilon, we can control. This involves one copy of pi and one copy of basis vectors. And so we can control this using a little bit of this, or a lot of this and a little bit of that, provided we put the sign on this. But I don't really care about the sign on this because I'm just going to control this by minus this constant times the norm of EL and the norm of En. And I can do the same thing with this term here. So more or less, this is because all norms on Euclidean space are equivalent up to constants. And so I keep this term, I throw this term away, and I bury all the other terms in some constant that is universal. It only depends on these ambient objects, not the choice of submanifold, and times a product of 2 copies of En and 2 copies of El, where I measure their size with respect to this Riemannian metric S. And so that's the sketch, the proof of the lemma. And so then if I happen to go to a point where I know something about the sign of this Laplacian, so for example, if I choose a point in direction that maximizes S locally, then I can infer from that the sign of this Laplacian is negative. And that, because this is positive, that means the sum has to be negative as well, which means that S dominates this partial trace of the Riemann tensor up to this kind of semi-universal constant. And so then this will be a long computation, but this is going to be the take-home result that we're going to need at the end of the talk, but we won't have much to say about it before then. Are there questions? Yes.
Why are you writing this for EM? Is this somehow like a special action?
Well, okay, at any point I can diagonalize S, but now I want to choose the point where S is maximal, and choose the point and direction where S is maximal over some domain, because that's going to give me a sign on the Laplacian.
No, I'm asking why is index of the vector En in the corollary and theorem is the same as like dimension?
Right. Okay, so I can choose to order the EIs in any order I want, and so let me order them in non-decreasing for S, and so then S En will be the largest eigenvalue, and then among such, and then I also choose Z, so the largest eigenvalue S is maximum. Other questions? Great. Okay, so now we can switch to the optimal transport phase of the talk. So, so I'm going to fix this smooth benefit function on a product of, say, 2 domains in Euclidean space, open, bounded. those are going to be the landscapes where my transportation takes place. And in some sense, you can think of the geometry of those landscapes. If there are mountains or lakes that cost a lot to go around, you would just embed that geometry in the choice of benefit function to be maximized. And I said I have these two probability densities. I can even think of them as being n-form densities, where the n-forms are mu and mu bar. And so this 250-year-old problem launches, let me look at the benefit of coupling x to f of x and maximize its expected value against at mu or rho. And Monge was thinking about Euclidean space, and he was thinking about minimizing the Euclidean distance between x and f of x, but and he was looking for a mapping that somehow maps this density onto that density, so pushes forward mu to mu bar. And the insight of Kantorovich from the first half of the 20th century was, first of all, I mean, you can reformulate this as a linear program if you allow each point here to pair with a continuum of points up there or several points. So if you don't insist things sit on the graph of a map, then you get a linear program, and that linear program has a dual program, and here it is, the dual. The dual says, let me look for pairs of a function u over here and a function u bar over there, such that the sum of u of x plus u bar of x bar is always bigger than the benefit xx bar. And among such pairs u and u bar, if I try to minimize the expectation, the mu expectation of u and the mu bar expectation of u bar, the minimum value I get will coincide with the supreme. And there's a sort of nice economic, so you can think of so f has this constraint that it's pushing mu forward to mu bar, which when f is a diffeomorphism turns into a condition on its Jacobian determinant. So up to orientation, the determinant of the Jacobian should measure the ratio of the supply taking place at x relative to the demand at x bar. And so on the one hand, you can think of the u as being, and the u bar as being Lagrange multipliers for the marginal constraints on the joint density here. So, and on the economic interpretation of u and u bar is that the idea is like, well, on the one hand, I could try to say who goes where to achieve this maximum. And on the other hand, what I could try to infer values. What is the value of stuff being produced at x, and what is the value of stuff being consumed at x bar? And then this inequality here that says the value of production at x plus consumption at x bar should dominate the benefit. Otherwise, there's sort of an arbitrage opportunity. So somehow the main measure of economics is that you can decentralize using prices, and up to signs, u is the price of goods to buy the good at x, and u bar is or maybe to sell the good at x, and u bar is the price to buy it at x bar. And then the question is, do I want to actually transport it and incur the cost of transport, or would I rather just sell what I'm producing at x and buy what I need at x bar? And this equality tells me that it doesn't matter which of these two things you do, you get the same answer either way. Okay. And so, it's not that after the work of Kantorovich, it's not that difficult to show that this supremum is attained by a Borel map, which a map F that has the property that on every subset V over here, the amount of production taking place on the preimage of V under F agrees with the amount of consumption taking place on V. But it's, on the other hand, it's a much more difficult problem to show that F has any smoothness. And that's the problem that Ma-Trudinger-Wang addressed in 2005. And they needed a bunch of extra structure in order to infer that F has smoothness. For example, in the case of Monge, the Euclidean distance, it's not true in general that F is smooth. Or even. I think there are counterexamples to continuity in 2 dimensions by Wang collaborators, Filipos and Ambrosio, maybe. So Ma-Trudinger-Wang said, let's restrict our attention to costs that are smooth enough. And moreover, they wanted this, if you fix x bar, when you take the x derivative of b, they wanted that to be a diffeomorphism between the domain and the tangent space. And they wanted its range to be convex for every x bar. And sorry, you fix x and you want x bar to be to be a diffeomorphism function x bar. And then for each x, you want the range to be convex. And actually, so far I've written this in an asymmetrical way, like I fixed x bar and I'm asking what happens. I fixed x and I'm asking what happens as x bar varies. I'm going to want actually the cost to be symmetric under interchange of x and x bar, so reflecting the domain range symmetry of the problem. And then if I have a curve with x bar varying and x fixed, I'm going to call that a B segment if its image under this diffeomorphism is an affine line segment. And so assuming that I have this, all the cost under interchange of x and x bar satisfies the same hypotheses, let me also ask, this is their condition A3, that if I have x bar t being a B segment over x naught and the mixed partial derivatives, where xs is any smooth curve, when the mixed partial derivatives vanish, I want the mixed fourth derivatives to have a sign. Somehow they introduced this condition, and then they said, under this hypothesis, the mapping that solves this problem will be smooth. Actually, so A1 was known earlier, so really what they added to this story was A2 and A3. And I should say that for one of the first classes of cost that people made a lot of progress on was the cost minus the distance squared. And for this particular cost, a regularity theory had been worked out in 2 dimensions by Delanoë and in higher dimensions by Caprelli and Urbas already about 10 years earlier than this. And this, somehow the regularity results of Ma-Trudinger-Wang are the first regularity results for an open class of costs. There's another class of costs that had also been investigated, which is the logarithmic cost that arises in the reflector antenna problem. Okay, so in the mid-90s, under this hypothesis A1, this diffeomorphism condition, it was already clear to Gangbo and I, and then to Levin, should be 1999, that a unique minimizer or maximizer to this problem exists. So this is max is attained uniquely. And what Ma-Trudinger-Wang add to this story is that if the densities are bounded away from 0 and infinity and smooth enough, then the mapping will be, in fact, one derivative smoother than the densities. And more or less what's happening is that we have this equation, determinant df. And the df under here is related to the derivative of u. So for example, for this cost here, in a special case, this would be the Monge-Ampere equation. And for other costs, there are additional terms. And this is a degenerate elliptic equation, and you can really only expect regularity for it if you can uniformize the ellipticity. But once you uniformize the ellipticity, you expect u to be 2 derivatives smoother than the rho and rho bar. And so the f, which is related to, in this example, it would be du, is going to be 1 derivative smoother. So somehow that's the arithmetic for this equals 1. And there are a lot of subsequent improvements on this. And let me also mention, in particular, this work of Lopere, which showed that if the closure of A3 fails, so if the inequality on the previous page goes the wrong direction, then you can actually find densities that are bounded above and below and as smooth as you like, but the map has discontinuities in it. So you get a picture like this, maybe. So in some sense, some sense, A3 is a sharp condition for smoothness. And okay, so the first thing I want to do is I want to reinterpret this condition A3 geometrically. And this was something that Jung-Han and I did in 2010. So if you think about joint measures on omega cross omega bar that project to mu and mu bar, then you can think of the support of such a joint measure, which is really telling you which x gets paired with which x bar so as to minimize the cost or maximize the benefit. And then you look at this 4-point function, which looks at the benefit of pairing x with x bar and x naught with x bar naught, and subtracts off what happens if you instead pair x naught bar with x and x bar with x naught. If gamma is going to maximize the benefit, then this function of 4 variables needs to be non-negative. So if x bar and x naught x bar are really paired with each other, then the benefit of this sum should dominate the benefit of that sum. And so although this is a function of 4 variables, let me think of it as a function of 2 variables. Let me think of x naught and x naught bar being fixed. And then let me Taylor expand this around x bar is close to x naught x bar naught bar. And because of the minus signs up here, the 0th order term is going to vanish. And the 1st order term is going to vanish as well. And some of the 2nd order terms are going to vanish. So if I take 2 derivatives with respect to x, say, and set x bar equal to x naught x bar, this term here will cancel that one. And similarly, if I took 2 derivatives with respect to x bar, this term here would cancel this one. But what does survive at 2nd order is the mixed partial derivatives of p. And then there are higher order corrections. And so what I want to do is I want to think of the Hessian of delta naught at x bar equals x naught x bar as being a metric tensor on this product space. And condition A1 is going to tell me that the determinant of H is non-zero. So it's an honest metric tensor. And on the other hand, if I think about keeping the sign of this perturbation fixed and flipping the sign on this perturbation, I'm going to flip the sign on the overall thing because this only involves products of the x and x bar variables. And so that tells me for every space-like direction for this metric tensor, there has to be a time-like direction and vice versa. And so that's how I come to the split signature. So the signature of the metric has to be n. And this condition on the submanifold tells me that the tangent vectors to the submanifold always have non-negative inner product with themselves. So the submanifold is at least non-timelike. And it turns out that the key to regularity is improving this non-timelikeness to spacelikeness. So we'd like to show that this inequality is strict. And then we would get then improve the degenerate ellipticity of this equation to uniform ellipticity. And in this particular example here, or the bilinear benefit, if you think about this what I call the cross difference, it just reduces to the inner product of the change in x with the change in y. And by the time you take 2 derivatives of this thing, you get the identity matrix in the x. If you can think of this as 4 n by n blocks, and you get 0 there. If you take 2 derivatives with respect to x, you get 0. Or 2 derivatives with respect to y, you get 0. If you take 1 derivative with respect to x and 1 derivative with respect to y, you get the identity matrix. And more generally, what this Hessian metric looks like is it's a block anti-diagonal matrix with zeros on the diagonal and the mixed partial derivative is transposed off the diagonal. And so it's always signature NN. So far, it depends only on the choice of cost function. We don't see that rho and rho bar at all. One of the observations there are several observations. So because of these 0 blocks, n by n blocks on the diagonal, when I go to the product of rho with omega bar, any vector that's purely vertical, like 0 plus p bar, is going to have 0 inner product with itself. And similarly, any vector that's purely horizontal is going to have 0 inner product with itself. And so this is sort of the light cone for this metric. And one of the observations with Jungian is that if I look at a fiber like this in the light cone, x cross omega bar, geodesic convexity of that fiber is equivalent to the convexity of dxb of x omega bar, a subset of R for every x. So in other words, if I pick a direction like this and I exponentiate it, I should stay in the same fiber. And because I assume symmetry under interchange of x and x bar, the same will be true of horizontal fibers. Yes, convex if hypothesis A2 of Ma-Trudinger-Wang is to hold. And one can also understand hypothesis A3 of Ma-Trudinger-Wang in terms of this metric. And so what Jung-Han and I showed is that the Riemann curvature of the two planes spanned by a horizontal and vertical vector, if they're orthogonal to each other, should be non-negative. That's exactly what it means for A3 to hold. Okay, but so far we defined our metric entirely in terms of the cost. We haven't invoked the densities at all. And what we did with Michael Warren was observe that you can put a conformal factor chi in front of this metric H, and you choose the conformal factor so that the volume of the new conformally equivalent metric is just the product up to orientation of the given forms mu and p bar on the two domains. And when you make this conformal change of metric, the result is that the graph of the optimal mapping or the support of the optimal joint measure becomes volume maximizing with respect to in its homology class. So for example, with respect to fact supported perturbations. In particular, it has zero mean curvature. So some of this is the connection between the plateau problem and the optimal transport problem. And the characterizations that I gave for condition A3 as saying something about the sign of the Riemann tensor for orthogonal pairs and the geodesic convexity of these horizontal and vertical fibers, they work equally well for the conformally equivalent metric that they did for the original metric. So somehow this is the natural geometry of the optimal transport problem. And right, so the proof sketch is going to have an echo of the talk this morning. So why should this thing maximize this funny conformally equivalent metric that I've defined? Well, there's an argument using a closed form that shows that it does. And the closed form is something that's just built out of the separate volume forms on omega and omega bar. And this is closed because, if you have, so it's made of an average of something like rho of x and a wedge of the x variables and rho bar of x bar and a wedge of the x bar variables. And so if you try to compute an exterior derivative here, the only thing that you can wedge into this without getting zero is an x bar variable, but rho doesn't depend on the x bar, so you get zero. So this thing phi is going to be a closed form. And that says that if so I have my sigma, which is in the example of the graph of the mapping. And I want to compare the area of sigma to what happens if I deform it a little bit. And in such a way that the difference between sigma and the deformation bounds a region. So because phi is a closed, I don't know, let me call this region lambda. Because phi is a closed form, the integral of d phi over lambda is going to be zero. But this is exactly the difference between the integral of phi on sigma and phi on sigma prime. And so these two things are going to have the same values. And then the other thing is that this metric has been, the conformal factor and the metric are, because the conformal factor is built so that the volume of this guy is the wedge of mu and mu bar, that's telling me that when I look at the calibration on a product of vectors vi, first of all, it's going to dominate the magnitude of the product vi. And secondly, equality is going to hold exactly on this submanifold. So the tangent manifold's built so that you get equality here. And so that tells me that on this side, I'm measuring the volume of the submanifold, and on that side, I'm getting something that dominates the volume. So this is sigma's volume maximizing. Okay. The V's here are tangent to the submanifold. And okay, so then the last thing that I want to do is talk about how having this geometric picture allows us to give a simpler proof of the a priori estimates of Ma-Trudinger-Wang for the regularity of F. And so in order to do that, I need to, maybe I could say some philosophy first. So initially we were a bit surprised that to find this unexpected pseudo-Riemannian geometry sitting in the optimal transport problem. And then because a posteriori, there's sort of an a posteriori rationalization for this, which is the same one as for why Lorentzian geometry comes up in the context of general relativity. And that is that somehow if I'm asking about this optimal mapping problem, and I ask, does it have a smooth answer or not? If the answer is yes in one coordinate system, it should be yes in all coordinate systems. And since A3 is almost a necessary and sufficient condition for regularity, A3 ought to have a geometrically invariant description. And this is the geometrically invariant description. Okay, so on the other hand, when I want to prove that F is smooth, I need some way to measure its smoothness. And so I want to introduce a positive definite metric on the domain and on the range. So let me take, for example, the Euclidean metric on the domain. And then let me use the inverse matrix in whatever coordinates I've chosen on the domain to define a metric on the range. So here's the inverse matrix. And then I lift from the domain to the range using the mixed partials of B. And again, let me put a conformal factor in front of the range portion of this metric so that the volume of S hat is again up to a sign plus or minus the wedge of mu and mu bar. And so once I fix these, a metric here and the corresponding metric on the ambient space, condition A3 is telling me that these Riemann expressions are positive for null P plus P bar. And so in fact, in any set of coordinates, I can fit a kappa in here where I measure the size of this vector with respect to the positive thing, S hat instead of S. And this is going to be just the internal, the what do you call it? The local regularity theory. So I don't want to talk about boundary regularity. And so I'm going to need a test function, which is compactly supported in the product of the two domains. Because I want to use maximum principal arguments, I want an interior maximum, not a boundary maximum. And and it's also an a priori theory that says, let me first assume that I have a smooth solution, and let me estimate the size of its derivatives. And then after I do that, you can, okay, so there's two steps. So there'll be estimates on the size of the derivatives of F. And as I mentioned at some point, the key issue is trying to uniformize the ellipticity of this equation. And what this means in this picture is my null cone looks like it looks like this. It's n-dimensional. And what I don't want is I don't want my sigma to be tangent to either the horizontal or the vertical fiber, because then the ellipticity degenerates, and it's just like in the Cheng-Yau Calabi problem where gradient U, you need to keep it away from the light cone. So basically the challenge to showing regularity is showing that the support of gamma, f of F, whatever, is bounding this away from the vertical and horizontal light cone. And the estimate in this theorem does this because it says the restriction of the sign metric tensor to the graph of F is bounded below by the positive definite guy and some constant that doesn't depend on F. It only depends on the ambient metrics and the test function and the L infinity norm, the C0 norm. So there's like a normalization that comes in as well. But apart from this, it's independent of mu and nu in the submanifold. And okay, for this theorem, you need F to be diffeomorphism, but how does the rest of the regularity theory go? The argument of Ma-Trudinger-Wang goes by local replacement. And so the idea is, now suppose that you had a not necessarily smooth solution F. Near any point on it, you would go to a small enough neighborhood at this point so that you have wonderful uniform convexity. and you would treat the values of the solution on the boundary as the data for a Dirichlet problem. And maybe it's not smooth and strictly convex, but you can perturb it a little bit to make it smooth and strictly convex, and then solve the Dirichlet problem and see that in the interior of this ball, you have a priori estimates on the solution, which are independent of the perturbations that you needed to do to make it smooth and uniformly convex. And so in the interior of this ball, you have good estimates. And on the other hand, you have a uniqueness theorem for solution to the Dirichlet problem on the small ball that tells you that the non-smooth thing that you started out with has to coincide with the smooth thing on a smaller ball. So that's how you get from the a priori estimate of the theorem to the regularity of optimal methods in general. Okay, so the last thing I'm going to try to do is sketch the proof of the theorem. Other questions? Yeah.
Let's say and the function of and the test function restricted on those.
I guess it depends on the test function restricted on sigma. I mean, we're not terribly careful about this. I don't know. I guess I should say I don't know. Okay, so the proof starts with the optimal dual potentials in Kantorovic's minimization problem. And for all x and x bar, this no arbitrage condition says that the sum of the prices has to dominate the benefit. And moreover, equality has to hold on the graph of the optimizer. And so then there's a first and second order condition on this graph. And the first order condition, if I take the derivatives with respect to x, it tells me the x derivatives have to vanish and the second x derivatives have to have a sign. And on the other hand, if I differentiate the first order condition with respect to x, I get the stuff that appears in the second order condition plus something involving the Jacobian matrix of F. And that's the thing whose determinant is controlled to be the ratio of rho to rho bar. And this, the determinant of this is also controlled by hypothesis A1, the diffeomorphism condition. And so if I take the log determinant of this entire expression, I get this kind of fully nonlinear expression in U. This term would vanish if I was a bilinear guy. And I get that that's equal to the log of stuff that I know to be bounded. And so in particular, I can already improve the second order condition to say that it has to be strict positivity. And what I really want is uniform positivity here. So if this guy's uniformly positive, then when I linearize this equation around some fixed solution U, I'll get something that's uniformly quick. So that's the goal, is to improve this to some uniform bound bigger than constant times S. And so you choose the point on the graph and direction that maximizes the largest eigenvalue of the product of the test function and S, the thing you're going to use to measure how big things are, relative to G, which is the guy you want to bound below. You'd like to say G is bigger than S. That would be telling me that I'm staying away from the vertical and the horizontal. And so you look at the expression you're trying to show is uniformly bounded, multiplied by the conformal factor. Let me call that lambda. And let me choose coordinates on the first domain, the source domain, Riemannian normal coordinates essentially, so that they diagonalize S. And so then when I this expression here, I can choose Riemannian normal coordinates, which moreover also diagonalize this thing, and let the eigenvalues of this thing be called lambda I, and then order them so lambda n is the largest one. And you can couple these directions with directions in the range using the Jacobian of F. And when you do that, you put the appropriate powers of the lambda i's in front of it. What you get by coupling these directions in the domain with the corresponding direction in the range turns out to be orthonormal for G. And if you think about the S inner product of EI and EJ, it still vanishes if I is different from J. And then because you have a 1 over lambda and a lambda, the eigenvalue for S is going to involve lambda I and its reciprocal. So with this ordering, actually, I guess it's mu n I want to be the largest. I'm now going to compute the Riemann tensor in these directions, EI and EJ. And so there will be some cross terms where you have ratios of lambda I to lambda n for the EIEN direction and lambda n to lambda I. There'll be other directions where you have, just multiple copies of lambda I, but you can control and lambda I reciprocal, and you can control those from below using mu I or mu n and some large but universal constant. And now I'm going to take this partial trace of the Riemann tensor. And so I'll end up with things like sum up to n minus 1 of lambda I over lambda n. And the domination of the means tells me that this is bigger than the product, the nth root of the product of the lambda i's. And on the other hand, it's the determinant of this that's controlled. So I would like to smuggle in an extra, I'd like to put lambda n here, and then I have to put an extra lambda power of lambda n down here. And similarly, there'll be a term with some of the reciprocals of the lambda i's and times lambda n, and you do the same thing with this term. And so when you do this partial trace, what you get is mu n to this extra power, n over n minus 1, slightly larger than 1, and times we had this product, this trace was bounded below by kappa. And then there's constants, these universal constants in the subtract the mu n's the largest of the mu i's. And on the other hand, in our first lemma, we had an upper bound for this trace at the maximizer. We had that this trace was less than, I'm thinking now of a test function which is like 0 on the boundary, but 1 in most of the interior of the domain. So you can sort of think of the test function as being 1. And this was less than something linear in the mu n's. And here I have superlinear, and I have it's less than something linear, and that tells me the mu n can't be too big. And that's my a priori bound. And I think all I have left is references. So here's the recent paper. Here's the original work with Junghan, the joint work with Warren. And I wrote a sort of survey of this in about 2014, of this sort of differential geometric and differential topological view of all transport. Thank you very much. So we can